Have you ever wondered why water takes so long to boil, while a metal spoon heats up almost instantly? This everyday mystery reveals a powerful scientific principle. Today we'll uncover the science behind how different materials respond to heat and what this means for everything from cooking to climate. Let's begin our journey by exploring what specific heat capacity means, see how it shapes our daily lives, and finally, reveal its role in heat transfer and calorimetry. To truly grasp why materials heat up differently, we need to understand the concept of specific heat capacity. This topic will break down its definition, formula, units, and why it matters. Before we dive deeper, let's define the term at the heart of our story. Specific heat capacity is the amount of heat energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius or 1 Kelvin. This definition sets the stage for understanding how different materials respond to heat. Here's how the specific heat capacity formula works, breaking down each part for clarity. The heat equation, Q equals mc delta T, calculates the heat energy required for a temperature change. The variables in the formula are Q for heat energy, M for mass, C for specific heat capacity, and delta T for temperature change. The SI units for specific heat capacity are joules per kilogram per degree Celsius, or joules per kilogram per Kelvin. Let's compare what happens when a material has high versus low specific heat capacity. High specific heat means a material needs more heat to increase its temperature, as seen in water and oceans. Low specific heat means a material heats up quickly with less energy, like metals and sand. Now that we've defined specific heat capacity, let's see how it plays out in real life. From boiling water to climate control, these examples reveal its practical impact. Imagine spending a day at the beach. You notice the sand is scorching hot, but the seawater feels refreshingly cool. This everyday puzzle is a perfect example of how specific heat capacity affects our environment. Let's explore why this happens and what it means for our comfort and climate. Here's how water's high specific heat capacity influences both daily life and global climate. Water heats slowly, which explains why boiling takes time and why oceans help moderate Earth's climate. Water stays warm for longer periods, making hot water bags effective and lakes slow to cool. Metals and sand, with their low specific heat capacity, respond rapidly to temperature changes. Metal utensils heat quickly, making cooking pans and spoons hot in a short time. Sand on the beach gets hot fast during the day and cools quickly at night, leading to noticeable temperature swings. Specific heat capacity also plays a crucial role in keeping our bodies stable and cooling car engines efficiently. The human body's high water content keeps our temperature steady, even when the weather changes. Car engines use water or coolants and radiators to absorb heat without overheating, thanks to their high specific heat capacity. With real-life examples in mind, let's explore how specific heat capacity shapes heat transfer and calorimetry. This topic reveals the science behind measuring and understanding heat flow. Here's how the principles of heat transfer are governed by specific heat capacity and related factors. Heat transfer depends on mass, temperature change, and specific heat capacity, as shown in the formula Q equals mc delta T. Materials with high specific heat need more energy to increase their temperature, as seen when water heats more slowly than iron. Calorimetry is the science of measuring heat, and its main principle is that heat lost equals heat gained. Calorimetry measures the heat exchanged when substances are mixed, helping us understand energy flow. The main principle of calorimetry is that heat lost equals heat gained, which is captured in the mixing formula. Specific heat capacity determines how substances respond when mixed, affecting temperature changes and energy storage. When mixing substances, those with high specific heat experience a smaller temperature rise, as seen when water heats less than oil. Materials with high specific heat can store more energy, making them ideal for radiators and hot water bottles. When mixing hot and cold substances, the one with higher specific heat has a greater effect on the final temperature. These daily life connections show how specific heat capacity shapes everything from weather patterns to cooking. Sea and land breezes form because land heats quickly while water heats slowly, creating temperature differences that drive winds. Oceans absorb and release heat slowly, helping cities near the coast enjoy moderate climates. Metal utensils heat up fast due to low specific heat, making cooking more efficient. Let's directly compare the effects of high and low specific heat capacity to see how they influence heating, cooling, and energy storage. For heat needed, materials with high specific heat require more energy to change temperature, while those with low specific heat need less. When it comes to heating speed, high specific heat materials heat up slowly, but low specific heat materials heat quickly. Cooling speed is also affected. High specific heat materials cool down slowly, whereas low specific heat materials cool rapidly. Finally, in terms of heat storage, high specific heat materials can store more heat energy, while low specific heat materials store less. Specific heat capacity isn't just a formula. It's a force that shapes our daily lives, climate, and technology. Whether you're boiling water, feeling the breeze at the beach, or relying on a car radiator, understanding specific heat capacity reveals the hidden science behind everyday experiences and global phenomena.